This is Lab 3 for Physics 1. The purpose of this lab was to start with the knowledge of motion and use that to find dp over dt, and then through the use of Newton's second law, find the net force acting on our system and to estimate the mass of a black hole given the initial position data for a visible star. The result was that I found the mass of the black hole to be 3.57669 e to the 31 kilograms. This was obtained by calculating the net force and using Newton's law of universal gravitation, which gives us this formula right here. How this is done and why I made the choices I did will all be explained later. So, since we were given the motion observational data for the visible star, we can say that the visible star near the black hole is our system. Those observations are contained in a CSV file and are used to find the net force acting on the star. The x and y positions of the star are recorded at a time interval of 1 Earth day, 86,400 seconds, which is our delta t. We also know that the mass of the visible star is 2.1344 e to the 27 kilograms. To help us with the analysis, we can start with the Python program. I needed to edit the code to put in the physics principles and concepts necessary to finding the net force on the star, including the parallel and perpendicular components of Fnet. The very first thing I did was to change star.m and delta t to their respective values. I then read the position data from the CSV file that contained my specific data and put that data into the x and y lists that you see right here. In order to find Fnet, we found change in velocity based on the first 3 position data points. The process is shown right here. By multiplying delta v by m, we obtain an estimate for the change in momentum, delta p. With that, we can calculate our first estimate of delta p over delta t, then apply Newton's second law to get our first estimate of the net force. We can get our next estimate of the net force at delta t later by taking the next motion data point and repeating this process. We would repeat this procedure over and over again in order to continuously compute a new change in velocity, which would be used to find a new change in momentum. And then Newton's second law will be used to find a new estimate for Fnet. So how is this done in our code? Well, here we estimate all the velocities we can from the position data. We create new lists to hold the x and y components of the estimated velocity. That's why our lists have one fewer entry than the number of position components. Then, using a while loop, we step through all the position data points using the index as the loop variable. This first part is where we calculate the x component of the velocity. This first line is for calculating the displacement, and then the second line is estimating the velocity by doing displacement divided by delta t. We had to edit the second half of the while loop, which is where we calculate the y component of the velocity, to this right here. Now, we can calculate the motion changes we connect to the net force. We used a while loop with the index as a loop variable. For each value of the index variable, we first formed v initial and v final from the velocity components in the list. Then, we needed to go through all of the steps to obtain delta p over delta t. All these lines had to be changed to what you see here. First, momentum had to be determined. We used star.m because that was our original mass. The change in velocity and change in momentum had to be computed. Then dp dt was estimated from delta p over delta t. And then finally, the last line was changed as Fnet equals dp dt, which is where Newton's second law was applied to obtain Fnet. This is where we linked the motion observations to the interactions of the system. We pushed this further by calculating Fnet parallel, which accounts for speeding up and slowing down, and Fnet perpendicular, which accounts for the curving of the trajectory, and linked those to the total pushes and pulls of the system. This line right here represents the parallel component of dp dt, which is the derivative of the magnitude of the momentum with respect to the time multiplied by the unit vector p hat. I changed the code for these steps to what you see here to make those calculations happen. Once we have dp dt parallel, we again use Newton's second law to connect the total pushes and pulls along that same direction. Using that, we found the Fnet perpendicular, using the code that you see down here. We have already included code to draw arrows for Fnet, Fnet parallel, and Fnet perpendicular, which you see right here. I chose to make the arrow scales much smaller, otherwise they would take up the whole picture and you couldn't see the movement of the star. I also chose to make 2 different arrow scales so that I could change the size of the arrows to fit the picture better. I proceeded to specify the interactions that contributed to the net force, which was the gravitational force of the black hole and the visible star. After doing all that, I was able to finally solve for the unknown, which was the mass of the black hole. As you can see from the code, I used the position vector specifically given to me to compute the radius and then plugged it into the formula that you see here to calculate the mass of the black hole. Now doing this pulled up a window of many masses, all extremely close together. The mass of the black hole is expected to vary a little bit due to the changing radius as you move along the elliptical orbit, since you are not a constant distance from the center, so all these different masses are to be expected. So in order to find a more concrete number for the mass, I decided to find the average mass of the black hole. I did that with this code right here, effectively finding the average to be 3.57669 e to the 31. So here is what you get when you run the program. The code starts right here and goes this way. The yellow arrow is Fnet, the blue arrow is Fnet perpendicular, and the black arrow shows Fnet parallel. You can see all of the masses listed here. And at the very bottom of the page, it shows the average mass. So, for the what does it mean? The three arrows you saw when I ran my program are the FNet parallel, FNet perpendicular, and the FNet. FNet is pointing in toward the middle of the hole. The parallel force is pointing in the direction the star would go, since it's like a tangent vector, and the perpendicular force is pointing perpendicular to the parallel, but still inwards like the FNet. Essentially, these three all give you the same values as their respective dp over dt's. You can see that because I set them equal to each other in the code. The difference between them is that the FNets cannot be observed because they are just forces, while the dp over dt's can be observed because they are looking at change in momentum over change in time. Now, the what if. If the mass was replaced and the motion of the observed star remained unchanged and is affected only by the gravitational force of the new black hole, I would not be able to tell the difference. The mass of the star, the difference in position between the black hole and the star, and the path would all stay the same, so there really won't be a large difference, and we therefore won't be able to tell the difference because all of our formulas would still give the same mass. And that is the end, so thank you so much for listening.